All right, cool. Let's jump in then. Last time we had finished up with screening for. We'd finished with screening example for our one-way ANOVA. All right, and let me pull this up. Okay. And so for our one-way ANOVA example, right? The idea is that we had some sort of experimental stimuli, right? An emotional eliciting stimuli. It's film stimuli, which is often something that's used to try and elicit affective states in participants within an experimental setting. But our question here is maybe we could have cultural, ethnic, racial background differences across these groups because these are American films. Our targets are generally sort of white, non-Hispanic individuals, and the question is do we see that this is perhaps people from different backgrounds may respond differently to these stimuli, and so maybe racial, ethnic identification is maybe something to take a look at in terms of things. Okay, so we had last time when we finished up worked through our screening, okay, and we had finished, okay, here. So if you recall, we didn't find, for this example, didn't have any missing data, no problem with accuracy or plausibility, so we were using our full set of 99 individuals. Here we're going down through taking a look at our distributions. Everything was looking pretty good. We had one person who was very low in my white non-Hispanic group, but everything else was looking all right. We noted here that we have our homogeneity of variance. Now, we only get into this when we're actually running our test. We request this with our ANOVA, so we didn't get to that. Just as a spoiler here, we're going to run into some questions about whether or not we violated our assumptions of unequal variance, but then down here, we've gone through and providing our recommendations, okay? So we went through, took a look, things were looking okay, and so now what we want to do is jump into the middle of our analysis, okay? So if you've got your one-way ANOVA set open and available to you, okay? Now mine, my SPSS, I guess, university just got the new version of SPSS, so there's been some interesting updates we'll get to in a moment on this, but what we want to do now, we've gone through and tested our groups. What we want to do now is go through and take a look to see if we have evidence for, broad evidence for differences in ratings of emotional valence and emotional arousal to this film stimuli, okay? And again, the question is do we have evidence that maybe this film is working differently for individuals from more diverse backgrounds, okay? So we're going to go to Analyze, Compare Means to One-Way ANOVA. And the handout we're using here is just this one, our One-Way ANOVA handout here. Okay. But I'll move that out. And so, actually, here, I'll move you guys out too, so I got a little bit more room. All right. So, what I'm going to do, ready to run my ANOVA model. So I've got emotional valence, emotional arousal. Those are my outcome variables. My independent variable, or my input factor here, is going to be my ethnicity variable. Okay. And then I'm going to go hit Options, and I'm going to ask for descriptive statistics, homogeneity of variance test, and then my Welch test. Does anybody remember what my Welch test is giving me? All right, do you remember what that Welch test is about?
No, I'm sorry.
So what are we using Welch for?
I wrote down in my notes. Oh, no.
Was it go
Sorry.
go for it, Rachel? Oh,
What is happening? Oh my gosh. I'm so sorry.
what's going on?
Sorry, I think my mic is being weird.
Okay. All right, Rachel, you were on it. What's going on with Welch's?
I just wrote down that it's recommended when you have unequal variances and unequal samples, and it makes does it make a correction to F in the degrees of freedom?
Yep, perfect. Okay, yep. So what we're going to do, we don't know yet because we haven't gone through and looked at this yet. So we don't know whether or not we're going to have violations of homogeneity of variance, but I'm assuming it's possible. And so what I'm going to do, even before I go through, is I'm going to go through and select this Welch's test. And what this is going to do is it's going to go through and just give me this corrected test, regardless of whether I need it or not. So I can go through and check and see if I do, and then kind of take things from there. Okay. So we've got descriptives, homogeneity of variance, my Welch's test. You can hit continue. If I wanted to change around confidence intervals and things like that, I could do that, but I'm not going to go do that. 95% is good. So I'm going to hit continue here. And then, depending on, with their new version of SPSS, it looks like they've gotten tired. I wield a lot of power in these in these YouTube videos that only you all watch. But apparently, the new version of SPSS now has the option to calculate effect sizes directly in it. So I'm just going to go through and click this estimate effect size for overall tests. Okay, and then I'm going to hit paste. All right, so I have this. I'll go ahead and label this as ANOVA test for my one-way ANOVA. Go through and run that syntax. And here we go. All right, so this is our output. So we start out with our descriptives, okay? I would always recommend requesting descriptives in this right from the start so we can go through and check to make sure everything looks sort of fairly consistent, right? And so if I go through and I take a look at these, at my the number of people I have in each one of my cell, notice that I do have an unbalanced design, right? It looks like I have about twice as many people in my largest group relative to my smallest group, right? But otherwise, everything else is looking consistent with what we've gone through and done in our screening, so that's good, right? Always want to double check to make sure who I've gotten in there is sort of working, okay? So we've got that. Then we're going to go through and take a look at our homogeneity variance tests, okay? And homogeneity variance tests, remember, our underlying assumption of our ANOVA model is that the populations from which we're sampling have equal variances on whatever outcomes that we're taking a look at, okay? Now, SPSS updated this test recently, again, that starts to become more in line with some of the stuff that you get in Stata. But what we're going to focus on, so these are a number of different homogeneity of variance tests based on sort of slightly different permutations. All you need to worry about is homogeneity of variance based on sort of the mean, so this first line, okay? And so Natalie, if you're looking at, I guess, so first, so Natalie, for these homogeneity of variance tests, do we want a small p-value or are we hoping for not a small p-value?
We don't want a small one, right?
Yeah, we don't want a small one, right? Because what is what is the assumption within
That
homogeneity of variance here?
the variances are different or the same.
The same. Okay.
Yeah.
And anytime we have an inference test, what is almost always the null hypothesis of any type of inference test? What are we testing?
If the differences are equal or not, or
Okay.
if there are differences or not.
Yeah, pretty much, right? Whether or not some value is equal to 0. Like that's almost always what we're testing, right? Is something equal to 0? And if we're looking and if we're interested in whether or not the difference in our variances is not equal to 0, we don't want it to be equal to 0, right? So as we're looking at this, Natalie, one more time, and then I'll leave you alone. What are you seeing in terms of this this test of homogeneity variance?
So it's this specific one on the screen.
Yeah.
Well, let's see. It seems that emotional valence, has much larger p-value than emotional arousal. So emotional valence probably for lack of a better word, passes the test, but emotional arousal does not.
Okay. Yeah. I think that's a good way in kind of general terms to think about this, right? Like anything else, when we're looking at that p-value, we think about this as evidence, a measure of continuous evidence against the null hypothesis, right? So for my emotional valence, I see my Levine's test for valence has a p of 0.158, which, Erica, what can we then conclude based on our assumption of equal variances across these different groups in terms of their rating of overall emotional valence?
The variances are fairly similar.
Oh, I could give you a hug. Yes, absolutely. Because what we would sometimes do is we would say, oh, that the variances are equal. But that's not what this says. It doesn't say that they're equal. It just looks like they're pretty similar, right? Or we just at least don't have evidence in these data to suggest that there might be some sort of concern about a violation of homogeneity of variance. So it's still like any other null effect. It's ambiguous. But for the purposes of our test, we're not getting strong evidence that we have a problem with homogeneity of variance. Okay. What about emotional arousal, Erica?
They look fairly different.
Yeah.
With the variances.
Yeah. And so we've got some evidence here that it's likely, or at least we have some evidence that in terms of emotional arousal, how calm to excited people are from our different groups are reporting sort of based on their reactions to this film, that we could have some differences across these groups. Okay. And so because of that, Riley, what are the implications as we move forward to take a look at our tests for this one-way ANOVA?
I don't know if this is what you're asking, but that we can assume that the emotional valence has not been violated.
Okay. And so because of that, can we go ahead and use our just standard ANOVA model?
Yes.
Cool. All right. And then for
arousal, since the variances are different, we might assume that they have been violated and we need to correct for that.
Yeah. And what test are we going to use for that?
A corrective one.
Yeah. Our Welch's test. Yeah, the one that we went through and requested in that box, right? So as we're going down through, we go through, and this is where in our screening summary, right, when we're talking about our homogeneity of variance, little evidence for violation of homogeneity of variance for valence, right? It's always p-value. You won't have clear evidence. There's at least nothing in these data to suspect we have a problematic differences in terms of the variability in valence ratings across my different groups. Okay, but for arousal, looks like I might have differences, right? And so that's something that I would need to go through and take and keep in mind. Same, I mean, if we go through and take a look at back in our screening, our graphs, we saw again our white non-Hispanic folks had pretty little variance on arousal. Our other groups varied much by quite a bit more, suggesting that we might have a more consistent response in individuals whose ethnicity, racial background match the target of the video versus those where there's a mismatch, which is an interesting finding and important in thinking about the validity of our manipulations and things. Okay, so going through and taking a look at our homogeneity of variance. So we go down here and take a look at our ANOVA table. Okay, Robert, in terms of our ANOVA table, if I'm looking at emotional valence, what am I seeing here?
What is the significant number or significance value for emotional valence? I can't read it.
Oh, okay. So are you on your iPhone?
No, I'm on my computer, but it's
it's
pretty
just,
small.
Okay.
For me, I don't know.
Right. So Robert, if you pull up this one-way ANOVA table or the handout, everything in that output is on there.
Okay.
Does that help see that a little bit better?
Sorry, I don't know. Sorry.
Okay, no worries. While Robert's working on that, Ari, what are we seeing in terms of our ANOVA output right here? What are we seeing in terms of emotional valence?
For our significance, it looks like it's for emotional valence. It's sorry, I want to say not significant. I'm blanking. But
right.
Better for that.
Right. Okay. So probably I would say that we do we have evidence against the null hypotheses based on our p-value here?
Yes.
So are you saying we have or we don't have evidence against the null?
Okay. We do have evidence against the null, right?
Okay. Flip that around. Remember that our small p-values this is evidence against the null hypotheses. Null hypothesis is that the mean valence score for each one of my groups is equal across all three groups. Here we have a relatively large p-value, and so what we would say is that there's not evidence against the null hypotheses here. Or we could say that these data are fairly consistent with the null hypothesis of equal means across our different groups. Okay? All right. So, thank you for trying to avoid just talking about significant effects or not. But you're on the right track. Okay. Now, what about, so for our valence, Ali, what is then kind of the conclusion that we would draw based on our omnibus test for valence here?
That the groups are not, that they're like not very different from each other?
I would say. I guess so. We don't have evidence against the null hypothesis. I would interpret this. It looks like reasonably similar levels of responding in terms of emotional valence across these different groups, right? Okay. Now, what about this test for arousal? Ali, what's going on here?
Aren't like very large differences, but it looks like it might be like approaching.
Okay. And this starts to get tricky, right? So if and people will be like sticklers, because oftentimes people will identify this as like a marginal effect or an effect that's approaching our benchmarks for interpretation, right? But then other people say, well, it's either approaching or moving away, one of the two. We don't know, right? And so people start to get a little bit finicky about that, interpreting these marginal effects. Regardless, we know based on what we've talked about in terms of S values, Bayes factor, this appears to be pretty weak evidence for a difference. But is this the test that we should be looking at anyway, given our homogeneity variance, the results of our homogeneity variance test? No, right? So if I go down here and I take a look at what's listed under robust test of equality of means, this is where my Welch's test is put down, okay? So I've got a Welch test for valence. I've got a Welch test for arousal. My Welch test for valence, I don't need to worry about that because I don't need it because I didn't violate the assumption, so I'm up here looking at my ANOVA. But for arousal, I did have evidence of potential violation of homogeneity variance. And so, Allie, if I go down through and take a look at my Welch test for emotional valence, what am I seeing?
Oh, yeah, there's some evidence.
Okay, perfect. So we've got what looks like some evidence of potential differences in ratings of emotional arousal across these groups. Okay, so really, like the screening, all the things we did in screening, that's lots and lots and lots. When we actually get to the actual test, it's pretty quick, right? We go through, we take a look at my descriptives to make sure those are all in line, right? That I don't have anything weird going on there. Drop down, take a look, see if I have evidence for a violation of homogeneity of variance. Sort of check that, and so that makes a distinction whether or not sort of where I'm going with stuff. And then I've got my ANOVA table and my Welch test. Sort of go through and interpret the appropriate statistics there, and that's it. That's all I need to do for this test. So the test goes pretty easy. So with these means-based tests, when you're going through, you're going to hit a number of different decision points. And these decision points almost always involve the extent to which I have evidence for differences in variance across different groups. Okay? If I don't, and then sample size too. Best case scenario, I don't have violations of homogeneity variance, and I don't have, and I have relatively equal sample sizes. If that's this case, I'm pretty good. If not, there are other things that I need to go through and consider. Okay. Questions about our test, what we did here. Okay. The only other thing that I'm seeing, I don't know if, again, University just released a new license for SPSS. I went through and downloaded it. What we have here now in SPSS is we can check that we want it to give effect sizes. And again, we see that we have for emotional valence, we have eta squared and omega squared for your fixed effect. Okay. This is your eta squared. Well, actually, I don't know that. Put a pin in that. I don't know exactly. I would need to go through and see what the formulas are, how SPSS is calculating this stuff. But my assumption is, I just found this out today. Here's your eta squared, along with the confidence interval around that. Here is omega squared with a confidence interval around that, right? Same thing, eta squared, confidence bound, omega squared, confidence bound for arousal. Okay, this is a big deal. Again, this is one of the things that I had specified was pretty cool about Stata, is because Stata does this. Apparently SPSS has got on board. Finally, it's been a while. There was no reason they couldn't have done this before, but now at least they're putting this on, so you'll have that available to you as well. Okay. Questions on that? All right. So here, bring you all back. You see your bright shining faces. Here we've got ANOVA. We've got going through, this is now again an older version of how we go through and do this, but this is how we go through, request our tests. This is our output with which we just looked at. Here is calculation of our effect sizes. Okay, so again, remember that for eta squared is just our sum of squares treatment over our sum of squares total. Okay, Rachel, can you remind me what sum of squares treatment and sum of squares total conceptually refer to?
I thought it had something to do, maybe I'm getting this mixed up with something about like, do you mean like what the value is, or are you looking more?
No, just like conceptually. So what does sum of squares treatment represent?
Is it like something like between treatments within treatments?
Yeah. Okay. Yeah. You're on the right track. So our sum of squares treatment, right? This is our sum of squares, mean squares, standard deviation. These are all measures of variability. So our sum of squares treatment, this is just the variability that we're seeing across our treatment means, right? Or across our group means, right? And what do we call variability across group means? What does that represent? This is part of our effect, right? If we're running these ANOVAs, we want to see that there is variability across my group means, because if I see variability across my group means, it means I have differences across my groups. Okay, so in our set, we've got variability between groups over the total variability, right? And so what we can do is we can interpret our eta squared as the proportion of variability, the proportion of total variability in our data that's accounted for by our grouping factor. Okay, so if I go through and I calculate eta squared for valence, and I calculate eta squared for arousal, right? I see that my eta squared for valence is about 0.043. For those of you who have any sort of reference or background in regression, is basically just an R squared value. Okay, we're saying that about 4.3% of the total variability in valence ratings is shared with my grouping factor. Okay, so my sort of differences in racial ethnic identity accounts for about 4.3% of the total variability, counts for about 4.3% of the total variability in the data that I have here, right? Same thing for arousal, count for about 5.8% of the total variability. Okay. Now you'll notice that these two numbers aren't terribly different, about 1.5 percentage points here, but we're still working with some pretty small samples here, some pretty small cell sizes. I mean, with our white non-Hispanic group we've got, and our black non-Hispanic group, so those are our two. We're pretty close there. We've got about 40 people per group. Our sort of non-specific other group is much smaller, right? So not huge differences in the overall effect here. But can anybody remember what our concern is with our eta squared statistics? What makes us a little bit worried about eta squared?
Is it because it can't be less than 0?
Yeah. And so if I'm going to err, Rachel, which way am I going to err?
Positively biased.
Right. And so what we're concerned about is our eta squared being a biased test statistic. Okay. Because I'm never going to get an eta squared that's exactly 0. And if it's not going to be exactly 0, even if in the population it is exactly 0, it tends to drift up. And so what we talk about eta squared is a good sample statistic. So for these data, what's going on? But what we're really calculating statistics for is to estimate population parameters, and this is where our omega test, or our omega squared statistic comes in. Omega squared, we still interpret the same way as we do eta squared. We would just go through and make sure to specify that this is a better population estimate as opposed to eta squared, which is sort of kind of telling us what's going on with our sample. Okay, so we'll see if I go through and calculate eta squared here. I've got a value of 0.022 and 0.038, so we see a significant reduction in that eta squared because we're still working with a pretty small cell sizes here. Okay, and so what I could do then, if I'm just focusing on arousal, because that's that's my outcome where I actually had some evidence that I may have some differences across these different populations. I would say that based on these data, we would estimate that about 3.8% of the population variability, or the variability in arousal scores in a hypothetical population of individuals across individuals who would watch this film, about 3.8% of the population variability in arousal ratings would be attributable to racial ethnic differences, at least sort of how we've gone through and done this. Okay, so again, we're still referring to this as a population estimate. It gets a little bit tricky because the people in my study may be the only people in the universe who have ever rated arousal ratings off of this particular film, but we're saying if we were to get, and again, then we start to run into problems, and this is a good way, this is why it's important to think carefully about this. So our groups here for this pilot are white non-Hispanic, fair enough, black non-Hispanic, fair enough, and then everybody else who was in our study who got all lumped together, which is not a reasonable sort of or interpretable group to go through and sort of put together. But if we have, say, everybody in the world, and we separate folks into black non-Hispanic, white non-Hispanic, and then everybody else, at least whoever's represented in our sample, we would say that division sort of maybe counts for about getting close to 4% of the total variability in population arousal ratings. So when you're thinking about the difference between eta squared and omega squared, what we're thinking is one is a more specific to the data that we're looking at, but probably some positive bias there. Omega squared is going to be a better population-based statistic. Questions? All right. Cool. So, Robert, Allie, for Stata, if we're doing this in Stata, what we do in Stata, you have to request your Levine's test separately. It's kind of more a la carte. You sort of ask for these individually. You type in Rovbar valence by whatever your group, or Rovbar, whatever your outcome is, by whatever your grouping variable is, and it will just give you your Levine's test. This first one here, this W naught, that's your F test for your Levine's. If you look and compare it to SPSS, it's the same test. Nothing exciting going on here. Same thing, we're requesting Levine's test for arousal by ethnicity, drops it down here. Okay. My ANOVA, so I have ANOVA valence ethnicity, gives me my ANOVA model for ethnicity. Here's my F statistic here for my factor. You see up here this R squared, that's equal to your eta squared. Okay, so you got it right there. For arousal, we found that we had a violation of homogeneity variance, or potential violation of homogeneity variance. So we're just going to, instead of an ANOVA like we asked for valence, we just ask for a W test. That's our Welch test. So we say W test, arousal, ethnicity, gives me my Welch test. Right. Here's some stuff that we can go through and use to get mean values and confidence intervals across our different groups. So we can go through, pull that up, start looking at that. And then we can use this E-stat E-size for eta squared, confidence intervals, E-stat E-size, omega, gives you your confidence intervals around omega squared. So gets everything put together down there. So go through, take a look, Robert, Ali. All this is detailed in the corresponding handout for these data for Stata, with some more notation and stuff like that. But if you have questions about that stuff, let me know. Right. All right. So how do we go through and write something like this up? Right. Something along these lines. Right. So first bullet here is just trying to sort of summarize what we found in these data, so kind of tying everything together here, and then down here going through and talking about trying to take all this information and trying to integrate it into some sort of comprehensive conclusions. So we say evaluation of responses to valence suggests that data are relatively compatible with the null hypotheses of similar scores across students of different racial ethnic backgrounds, right? And then just throwing in a bunch of our statistics. We don't really need to do much more after that, right? We're just saying, yep, based on our data, null hypothesis seems reasonable based on the tests that we've got, right? We don't have strong evidence to say, to identify differences. This isn't saying that there are no differences. We're just saying that the data that we've got makes it seem like the null hypothesis is pretty reasonable, so no reason to go off additionally into that, okay? But then we're saying Welch test for ratings of emotional arousal demonstrated some evidence of possible differences across white, non-Hispanic, black, non-Hispanic, and heterogeneous other groups, right? Again, providing all our statistics, right? Our estimates of omega squared suggest approximately 3.8% of the population variability in ratings of arousal can be accounted for by racial ethnic differences across viewers, okay? So notice here that what I'm doing is I'm making sure that my reader knows that this is, my omega squared is a population-based statistic, right? Following correction for unequal variances, calculation of Bayes factor indicates odds of different responding across groups are at most 200% more likely than the odds of equal ratings across populations. Here, trying to pull in some of my Bayes results of my Bayes factor to try and sort of talk about sort of how much confidence, sort of best case scenario, my alternative hypothesis is about 200 times more likely than my null. This isn't strong, overly compelling evidence, but it's something, okay? So we'd say whether these data are limited by modest samples, the inclusion of homogeneous other. Oh, that's. Hey, CJ.
Yep.
Can you send me an email to change this? This should be heterogeneous other, not homogeneous other.
Yep, sounds good.
Yeah, this is my catch-all. So my heterogeneous other student group results offer preliminary support for differences across racial ethnic groups in some domains of affective response to a standard film stimuli, right? So we're just trying to take this together and sort of for whoever's reading this to say, hey, these are kind of our conclusions, right? Don't have strong evidence, but at least some indication that we may see differences in some aspects of affective responding based on different types of backgrounds, which if I'm using these stimuli to elicit emotional reactions in a study, particularly if we're working somewhere where we've got people from a lot of different backgrounds coming in, what I might say is this might be a more consistent experimental manipulation for folks where the target of the film or the person who's rating the film are similar in characteristics with the target and actor of the film, which could be something to reasonably think about. Questions on what we did here, how we tied this all together, anything along those lines? Feeling okay with this? Okay, cool. Let's do this. Let's go through, take a quick break. Why don't we come back at 3:10 and we'll jump into some details about what we do once we get this omnibus test taken care of. Sound good? Okay, cool. See you all in about 10. So I got good news. My roofers are gone. So considerably easier to concentrate on things that are going on here. So I'm excited about that. All right. Questions about what we've done up to this point with ANOVA means-based testing, anything up to this point? You comfortable with this? Okay. I just show hands. Is this starting to ring bells, bring things back to people from undergrad stat courses, sort of working through ANOVA, sort of understanding some of the stuff that we're trying to do with these analyses? To some extent? No? Ari looks skeptical. Everybody else looks relatively neutral. Okay. Well, good. Maybe this is all new stuff, which is exciting. It's exciting days for you. New stuff with means-based testing. Okay. All right. So, went through with this initial set. took a look at differences across these groups, which is good. But is anybody left here feeling a little bit unsatisfied or feeling like things aren't totally clear? What do you think, Robert? Is there stuff that you'd like to know beyond this? Based on sort of the test that we've run here.
Yeah.
Yeah, what else would you like to know? So here, based on our ANOVA, I'm saying, yep, it looks like there are differences in ratings of emotional arousal across different groups. What else would
So we want to know.
What's that?
I was gonna say maybe like the magnitude or like how large or the difference is.
Okay, so we do have that a little bit. So we've got this omega squared. That tells us kind of the magnitude of effects. So I'm saying, essentially, I've got, hey, Robert, I got these 3 different groups. They're different. What else might you want to know?
Oh, we want to know like which groups are different.
Yeah, right. Which groups are different than which groups, right? And this is what we don't get with our omnibus test. Our omnibus test tells us that at least one the means of at least one of the populations from which the samples were drawn is different from the rest. Okay, our omnibus test is just saying that there's a difference in there somewhere, but we don't know where that difference occurs, right? If we want to determine where those differences are at, we need to get back into these data and start to go through and start to make specific tests. Okay, so our omnibus test is a nice way to go through and say, yeah, there are differences somewhere, but it doesn't tell us specifically who's different than who. Okay, and so our classic approach to ANOVA requires that we have an interpretable F test before moving into the follow-up test, right? So from the traditional approach to this, we would say that if I don't have evidence against the null hypotheses, right? If everything looks up and my data appear to be relatively consistent with the null, my rationale for jumping in and looking at differences across individual means starts to become pretty questionable. Okay, the idea being if I don't find an overall difference, why would I be going through and starting to pull apart? So, oh well, overall I'm seeing my data is telling me I don't have strong evidence of a difference. So why would I go in and start saying is A different than B, is C different than A, that type of stuff, right? The concern is from a traditional standpoint that sort of there's fishing going on here, right? But Howell and a number of other methodologists will argue against sort of this general approach and sort of the overall utility of this omnibus F. Okay, and the argument is that if I've got, let's say, Brittany, a situation where I'm looking at, say, I've got 5 different groups. Okay, I've got 5 different conditions. And conditions A, B, C, and D are all pretty much the same. And then E is different than the other ones. Overall, with that many groups, what can happen is that sort of that difference between that one group and the others, particularly if it's fairly subtle, starts to get lost in the fact that the majority of groups are all kind of equal to one another, right? And so there's some concern that this overall omnibus test can start to get diluted by a bit. Another concern with this is that if I go through and I include, so we're going to get into how we go through and correct for tests, but that omnibus test is a test in of itself. And if I go through and I correct my test, or correct and include that omnibus test in my follow-up tests, what I start to go through is I start to set a pretty conservative bar for identifying evidence for the effects that I'm interested in, right? And remember, from a conceptual standpoint, right? Erica, is there such a thing as a type 2 or as a type 1 error? Are groups A and B are coefficients ever going to be exactly equal to 0? No, right? And so we've got this big concern with type 1 error, which is sort of good, but sort of argument is, well, you can't make it type 1 error because type 1 errors don't exist because nothing's ever going to be identical, right? And so what we do in our particularly in social sciences, right, which are our errors that we make most of the time are type 2 errors, failing to detect evidence for things that are there, although they might be pretty subtle, right? And so the concern is if I go through and I'm doing an honest job and correcting for all the tests that I conduct, and then I start going through and adding the omnibus test on top of it, starts to become overly stringent in terms of my correction. And then the argument for that Howell and some others will make is that our omnibus test is rarely of any practical interest, right? The omnibus test is never like you're never going to read a paper that's like, hey, we're just interested in if these conditions are different than one another, right? And then I go through and I say the conditions are interested in one another. Like, cool, that's all I wanted to know. I'm out, right? This is not what goes on, right? And so you'll see in some fields, particularly psychophysiology, some areas will just straight up ignore the F and go straight to whatever hypothesized a priori pairwise comparisons are of interest. Okay, so the traditional approach is that I can't move forward with follow-up tests unless I have evidence of differences based on that overall omnibus. But Howell, other people will make the argument that who cares about the F? That's just another test you have to run. If my hypotheses are that groups A and B and groups B and A is different than C and B is different than C, why screw around with the omnibus test? Just jump in and run those tests specifically as individual contrasts. Okay, so just a couple different perspectives, right? But recognizing that there are different ways of looking at and thinking about sort of the utility of the F, right? So we had talked about at the sort of start of last lecture that we had said some benefits of this ANOVA model is it's more efficient than having multiple tests. Well, if I do find that there's differences, I got to go run through those multiple tests anyway, right? And some originally we had said, well, this avoids complications with type 1 error because I can run that omnibus test and it sort of does everything, sort of consolidates everything. It's like, well, sure, until I get an effect, an omnibus effect, then I got to go through and see where that's going on. And so now what I've done is I've run an omnibus test, and I'm going to go through and run the pairwise test that I'm interested in anyway. So I've actually added maybe some tests in there, right? And so really what we're left with is the primary benefit of our ANOVA designs is just greater flexibility in interpreting results and designing our experiments. So with my omnibus test, I can say, yep, overall it looks like these groups are different, and then I have to go through and get into the mix in terms of teasing out what's different than what. But at the end of the day, I still have to be thinking about multiple tests and type 1 error, because as soon as I get into some of these other tests, I start to rack up the number of analyses that I'm doing here. Okay? So people kind of see from a conceptual standpoint, sort of, again, no free lunch. We thought we were getting something good, but then actually when we go through and do find stuff, then we got to move forward and run through some pairwise stuff anyway. So what we need to be doing with these designs is start thinking about how we manage this type 1 error. Okay. And if we're talking about, so just so we're straight on our terms, if we're talking about per comparison error rates, per comparison error is the probability of committing a type 1 error on any given test. So Brittany, remind me what a type 1 error is again?
False positive.
A false positive. Explain that a little bit more to me.
That's when you claim one thing. You claim that there is a difference when there's not.
Yep.
Is that correct? Okay.
Yeah, that is correct, right? And so what we want to do, because we're scientists and we're conservative, we don't want anybody sort of getting away with making a career for themselves with data for the effects that aren't replicable or can ever sort of be found again in a universe, right? Still happens. But so this type 1 error, our alpha level statistically is intended to control for the probability of type 1 error. Right? And usually this is going to be 0.05, right? This is going to be a little bit different than our error rate per experiment, right? Our error rate per experiment refers to the number of type 1 errors across a set of comparisons. So if I'm, say, running 5 tests, right? I keep my alpha at 0.05 for test 1. I keep my alpha at 0.05 for test 2, 0.05 for test 3, 0.05 for test 4, 0.05 for test 5. But the likelihood of me making at least one type 1 error across those 5 sets isn't 0.05. It's something quite a bit larger than that. And if I go through our error rate per experiment, if I've got 5 tests, if I take 0.05 times 5, I'm expected to make my error rate per experiment on this is 0.25, right? Which is setting a sort of a much more higher likelihood of making a type 1 error across those 5. Each one of those controlled is at 0.05. Okay, so we're going to get into our family-wise error. Okay, our family-wise error is the probability. So here, our per comparison, we're talking about probabilities. Error rate, we're talking about numbers. Family-wise error, we're back to probabilities, talking about the probability of committing at least one type 1 error across a series of comparisons. Okay, and we calculate our family-wise error a little bit different than we count for our error rate per experiment. Family-wise error is given as 1 minus alpha to whatever the number of comparisons we have here. Okay, so for 4 comparisons, each test run at 0.05, my family-wise error rate is 0.185. So what I see is that my family-wise error rate is going to fall somewhere in between alpha and somewhere times my error rate per experiment, right? But we're generally assuming that it's going to be close to that C times alpha level. Okay, and we're going to see this C times alpha thing come back up. It's involved in so we'll use this. We'll see this in our Bonferroni equality, our Bonferroni inequality that we'll use down the road for our Bonferroni correction. Okay. So this is getting into some technicalities of our error rates. The take-home message is here that as we start to go through and conduct a number of tests, the more tests that we run, particularly if we're looking at a pretty big design and looking at a bunch of different pairwise comparisons, the likelihood of me making at least one type 1 error, saying that I have an effect when there isn't actually an effect to be had, it's just sort of I made a mistake, starts to increase with the number of tests that we go through and run. And so what we need to be thinking about doing is going through and managing this in some way. So, as we're approaching our follow-up tests, we run our omnibus, right? We find evidence against the null hypothesis. We're seeing that it looks like there's a difference in there somewhere. How do we move forward? Okay, some general recommendations. Number 1, be selective. Okay, look at comparisons that are meaningful. You don't necessarily have to test all pairwise or all possible pairwise comparisons. Almost always, all possible comparisons are not going to be interesting. There's going to be groups that it doesn't matter, and even if you did find a difference, it would be hard to explain why those groups are different anyway, right? You're going to run tests against other groups that aren't going to be interesting, right? You're going to find back, oh yeah, those are different. Well, no duh. Like, of course they are. Like, of course everybody, it's not an interesting comparison to make, okay? And so the problem with going through and testing all possible pairwise comparisons is it starts to waste power, because if we're going to test all those pairwise comparisons, we probably ought to be correcting for those. And if we're correcting for 6 pairwise tests when we're only interested in 2, that increases my threshold for identifying stuff, and so I'm wasting power, and it's also going to make things super complicated. All right, you're going to see this, right? If you go through and you run tests in a paper and you find that there are differences, you're kind of obligated to talk about those differences, because if you ran it, I'm assuming that you thought it was interesting. Now you have to tell me why it's interesting or why this difference makes sense, okay? And if you've got a big design and you run all possible pairwise comparisons, a lot of stuff's going to come up that's not interesting, that you don't want to talk about. But if you ran the test, I'm assuming you ran it because it was important. Now I want you to tell me about it, right? And so being careful, it can really, really complicate an otherwise straightforward story. Okay, and so what we want to do is we want to choose a strategy that manages your family-wise error across our planned and unplanned comparisons. Okay, so sometimes when we're doing, or most of the time when we're running these tests, there's going to be stuff that we a priori predicted, right? There are certain contrasts that were important for my study. Like this is the whole reason I put this study together, right? And so these are the things that I'm calling my shot ahead of time. I'm saying group A is going to be different than group C, and group B is going to be different than the combination of A and D, right? That's really sort of at the heart and soul of my hypotheses, right? So those are going to be my planned comparisons. But there could be other tests that I want to run back. Oh, well, so this is a more exploratory thing. I want to go through and conduct these. Well, those we're probably going to start penalizing a little bit because they're sort of exploratory in nature, right? What we would need to do is come up with some sort of plan to say, okay, this is how I'm going to manage this type 1 error. SPSS won't do this for you, okay? SPSS is just going to go through and correct for everything if you ask it to correct for everything when you might not want it to correct for everything. And so it takes sort of some planned, effortful approach to go through and say, okay, which ones are my a priori, my planned comparisons, which one are my exploratory, and then I need to come up with a strategy that kind of manages this. Okay. So number one recommendation is just to have a good reason for examining the comparisons that you're taking a look at, right? Just have some sort of reason. If I were to say, Rachel, tell me why it's important to look at these contrasts that you've done, you could say, this is from a theoretical standpoint, from a practical standpoint, from a method standpoint, this is why these are important tests to make. And this is what I think is going to happen or should happen sort of based on X, Y, and Z. These other ones, these are exploratory. They could be relevant for this or that. This is why we conducted them. But if you ever get into a point where you're trying to run through a results section, you're having a hard time trying to come up with a reason why we looked at X, Y, and Z, aside from the fact they were there and we could, you've probably gotten yourself into a sticky situation. Again, saying the fact that you're able to do something, rarely sufficient reason for actually doing it. So it's good just life advice for a number of different things, right? But particularly when we run into these analyses that can be quite big, want to have a clear plan and a clear reason for why we're looking at the things that we're looking at. Questions on this general approach? Okay. All right. Wilkinson, 99. I don't know. You're like, this is Gandalf. So I hear this in Gandalf voice in my head, right? Rachel, I want to just take you're always very impressed with my music. It makes me happy. So the level of excitement you have for this. But I think it's good. So saying researchers rarely need to compare all possible means to understand the results and assess their theory. By setting sites large, they sacrifice power to see small, right? Looking at this, lattice of all possible pairs is a straitjacket, and again, forcing them to wear it restricts researchers to uninteresting hypotheses and induces them to ignore more fruitful ones. If a specific contrast interests you, examine it. If all interests, ask yourself why. Okay? This is a hard thing to do because I've got these data, right? And why don't I just look at all the comparisons, all possible? Let's see what's different than what, right? The problem is, at the end of the day, I'm going to have to explain this. And I'm going to have to interpret this and sort of bring this all together and tell a story, right? If I've got 2 or 3 comparisons that are central to my hypotheses, that's an easy thing to go through and do, right? If someone else wants to look at those other comparisons, go nuts. I'm going to report my mean, standard deviations. Cool. You do you. For me, these are the things that I'm interested in, right? If I go through and I start running, 8, 10, 12 different comparisons, now I've got a lot of stuff to talk about and a lot of stuff to explain, right? So just be judicious as you're thinking about which of these comparisons do I want to make. All right. So for my follow-up test, we're going to separate these into a priori tests and post hoc tests. My a priori comparisons, these are going to be, and again, it's going to be a small set of theoretically meaningful comparisons that I choose to conduct before my data are collected. Okay, so right now I'm assuming that So Allie and Robert and I in weekly meetings, we're going through and talking about thesis ideas and different studies and things along those lines. We don't know what those are going to look like yet. I assume that you all are probably in the same boat, sort of going through and doing things, but it could be that one or both of them come up with some sort of experimental design, right? And we're saying this is the research question, this is what I'm doing, and what we'll do at some point is say, okay, these are the comparisons that we think are going to be important, right? So before I even go through and start collecting data, I'm going to say these are the groups that I want to compare in this ANOVA design, and this is what I think is going to happen. I'm not only just saying these are the groups that I want to compare, I'm also going to make a prediction to say this is the direction I think this is going to go. Okay? And what we can do, if we're taking the traditional approaches for these a priori comparisons, right? This is you calling your shot before you even collect the data. What we're going to do is we're going to evaluate these as a set of linear contrasts or independent sample t-tests. And what we're going to do is we're going to conduct these at per comparison error rates. All right. The idea is that if you've gone through and called your shot before you even started collecting your data, right, we can go through and evaluate these as per comparison error rates. You're getting credit for calling your shot before you even did the data collection. This is a priori. I had no data to go off of. This is just my theory-based sort of conceptualization of, if my hypotheses are correct, this is what should go on. Okay. Now, some people will argue correcting for family-wise error with a Bonferroni or Dunn-Sidak correction. We'll talk about what those are. This is a more conservative approach, right? And something we can think about in terms of, and something that a decision that should be made beforehand. But technically, from a traditional standpoint, if I've made a priori predictions, and not like 15 a priori predictions, that's not good, but like a small set of a priori hypotheses, I can move through and look at those at per comparison error rates. So no correction for these tests. Okay. Post hoc comparisons, on the other hand, these are comparisons that you've decided to make once the data are collected and after you've looked at them. Okay. This often involves an analysis of all pairwise comparisons, right? What goes on here is Natalie's gone through, she's collected the data, and she's looked at kind of what those mean values are, and then starts to say, oh, I wonder if this is different than that, right? Or I wonder if I have evidence for this group being different than this other group, right? Now, Natalie didn't think about that before she saw the data, but she saw that, hey, this group was a lot different than this group. I wonder what that test would look like. What you've done is essentially you've ran all possible comparisons in your brain already. You looked at it, right? You said, oh, these are the ones I want to look at. Probably not because they're similar. It's probably because they're quite different, right? And so what's going on is that starts to throw off our error rate. So we're capitalizing on chance here, right? And so what we've got is some post hoc procedures that are used to incorporate a correction for that family-wise error that go through and essentially assigning a penalty for not calling your shot in advance. You're capitalizing on chance, right? You're cherry picking the stuff that looks most different from one another, which increases the likelihood of you hand picking things that are just likely to have just randomly been different just because of sampling error and things along these lines. Okay, so my post hoc comparisons, I can get these really easy in SPSS. Problem is SPSS is going to correct for all possible comparisons, even if I don't want to correct for all possible comparisons. So we need to be careful and planful as we're going through and running this type of stuff. All right. In general, and again, I don't want to sort of keep harping on this, but I can't emphasize this enough. Having a limited set of planned a priori contrasts is the methodological high ground. It's the more theoretically defensible approach. Okay, it's good science. If you decide that you need to look at all possible pairwise comparisons, you need to have a should have a very, very compelling rationale for why it's important to look at all possible pairwise comparisons between all possible groups. So, otherwise, it seems the appearance is either one of two things. One, you didn't think carefully about your study before you ran it, or two, you don't really understand what you've done or why different things should be different than one another, Or 3, you're just on a fishing expedition and just trying to find what's different than what, so that you can claim evidence for an effects without having a good reason for why those things should be different in the first place. Okay? And if you publish and you're going through, you'll run into sometimes with reviewers where they say, well, you didn't look at groups X or Y or groups Z and X, or sort of why didn't you look at sort of whether these groups were different than that group. What you can say at that point is that those weren't relevant to my hypotheses or my study. Those weren't central to the aims. I've provided means and standard deviations. If people are interested in comparing those, they have enough information to go through and make those comparisons if they want. For me, I was trying to manage my risk of type 1 error, and so I limited to a set of a priori hypotheses. If people want to go through and take a look at it, cool, they can go nuts, but it's not relevant. I don't want to have to talk about it or explain why these are important because I don't think they are. Okay. So again, as you're going through and putting together projects and papers and sort of using data that you'll collect or stuff that you'll or stuff that may be existing in your lab before you go through and actually start running these analyses, I would encourage you to think carefully about which groups do I think are going to be different from which groups. Think that out, plan that out first, and then jump into the analyses, not before. Okay. And again, it's just good science. All right, so my planned comparisons, right? Simplest way to approach this, and sort of the traditional approach to looking at pairwise contrasts in ANOVA, is just with a independent sample t-test. Okay, independent sample t-test with a follow-up test looks, the structure is the same. We're just plugging in a little bit different values here. If I've got a situation where I've got relatively equal cells and relatively equal variances, so my individual cells that I'm going to be comparing are about the same size, and the variability so I haven't had a violation of homogeneity of variance, so we start to see where homogeneity of variance starts to become an important consideration. But if I've got relatively balanced design and I haven't had a violation of homogeneity of variance, and I'm interested in whether or not I have pairwise differences, what I can do is I can just essentially just run a t-test between those two. And for a follow-up test, for a priori pairwise comparisons in following ANOVA, our test statistic is just going to be equal to the deviation between our two means. So I'm comparing mean of group 1 and mean of group 2. And then I'm taking that over my standard error estimate is going to be my mean squared error over the top of the number of people in cell 1 over mean squared error, number of people in cell 2. Okay, and this mean squared error, this is taken from my ANOVA table. Okay. So for, let's say, our group here, right, the one that we just went through and did, if I wanted to see whether or not I had differences in arousal ratings across my white non-Hispanic and black non-Hispanic group, right? Relatively similar, sort of difference of 3, so they're relatively equal. Now, I've got a violation of homogeneity of variance, so that kind of throws a wrench into this. But let's say I didn't, right? What I would do is I would go through and I would take the difference between my white non-Hispanic group and my black non-Hispanic group, and I would take that over my mean squared error pulled from my ANOVA table, divided by the number of people in my first cell, and then I would take my mean squared error divided by the number of people in my second cell, and I would use that to calculate my standard error. Okay. Now remember, from our independent sample t-test, our independent sample t-test is just the difference in group 1 and group 2 over pooled variance. Pooled variance over the number of people in cell 1, pooled variance over the number of people in cell 2. Again, this is just saying using our mean squared error from our ANOVA table as my estimate of within group variability. Okay. And then what I would do is I would compare my test statistic against a critical t value with t alpha divided by 2, so 0.05 divided by 2, so a two-tailed test with degrees of freedom error from my ANOVA table. Okay, so once again, if I go down through and I take a look at my degrees of freedom from my ANOVA table, degrees of freedom error is going to be 96 here. Okay. So what we see with this approach is this use of our mean squared error and corresponding degrees of freedom gives us a more powerful test of these simple effects. Can anybody look at this and tell me why this approach is giving me a more powerful test? So let's say, Allie, let's say I'm wanting to go through and I want to look at, in our example that we ran through, I want to look at my white non-Hispanic and my black non-Hispanic groups. And I'm just going to run an independent sample t-test. Okay, what's the degrees of freedom on that t-test going to be? Okay, I saw you waving around the number 2 in your face. So I think I couldn't hear you. What? Yeah. What did you say?
Oh, I just said you cut out for a sec, so I didn't get what groups you were comparing.
Okay, so let's say I'm just going to run an independent sample t-test against my white non-Hispanic and my black non-Hispanic groups. What's the degrees of freedom for that test going to be?
Oh, n-2. So I can't do simple math. So it's going to be 60 or 77.
77, right? Okay, so my degrees of freedom for that independent sample t-test, if I were to just compare these two groups, is going to be 77, right? But for my comparison here, my critical t is going to pull degrees of freedom error from my ANOVA table. And so if I pull from my ANOVA table, what's the degrees of freedom error for my ANOVA in my ANOVA table?
Just 2.
Is that?
Or
yeah, degrees of freedom error.
Yeah, just 2.
Okay, this is my between groups. This is remember that between group variability is my effect. Within group variability, what's that?
Oh. So
96, okay? Because remember that within our ANOVA designs, any differences that we're seeing within a cell is due to error, right? Because it's something that we haven't accounted for, right? So our degrees of freedom error is going to be degrees of freedom within, and so it's 96, okay? And so in our t-test, our degrees of freedom, if we were to just look at these two groups, is going to be a difference of 70, or we're going to use 77 degrees of freedom here. If we're using and capitalizing on the full design, my degrees of freedom for this test is going to be 96. Okay, which one of those gives me the smaller critical value? 96, right? I'm using more degrees of freedom. I'm using all the degrees of freedom within my design instead of just using the degrees of freedom across my two groups. Okay, and so this approach goes through and we're using the degrees of freedom from our overall ANOVA for my test to test against versus just my two groups, which my two groups is always going to be a smaller degree of freedom, which means that sort of my critical value is going to be larger, which means I'm going to have to get farther out there before I can claim evidence for an effect. The other thing that we're doing is we're substituting our what we would normally use as our pooled variance with our mean squared error. And remember that our mean squared error here is just the aggregate estimate of within group variability across all of my cells. Okay. Now, if I haven't violated homogeneity variance, my assumption is that the variability of whatever I'm looking at is equal across my different groups, right? And so if I'm using my mean squared error, there's more people, because this is utilizing my whole design, right? So instead of 79 people, that go into calculating my error variance for my independent sample t-test. Here, I've got 99 people, right? And if I'm assuming my variance is going to be equal across these different groups, which gives me the better and more stable estimate of variance? The sample that's limited to just the 79 folks in my two groups, or the full sample of 99 folks? 99 folks, right? And so what we're doing with this traditional approach is, if I've got a good design where I've got relatively equal cells, and I've done a pretty good job, don't have clear violations of homogeneity of variance, the traditional approach to pairwise follow-ups within ANOVA is to just use the mean squared error from your overall ANOVA table as your error as an estimate of your error variance, and then use a critical value based on the degrees of freedom for your test, which gives me a more stable estimate of my variance and a more lenient critical value, which should on average produce a more powerful test. Okay, so again, what we're doing is you're getting credit for calling your shot in advance, and then 2, running a good balanced study study where we're not having violations of homogeneity variance and things. Okay. Do people kind of see sort of what benefits we're getting from this? But oftentimes, we're working with analyses where we don't have equal cells, or we have unequal variances. If this is the case, it's fine to just drop back and just use our independent sample t-tests with pooled variance, or our Welch-Saterwith correction on those, just basically going through, and which is probably what I would elect to do in sort of our example here, because we've got, it's not completely balanced, right? But we do have evidence of homogeneity, violations of homogeneity variance. It might be difficult for me to make an argument to use sort of this test. And so what I probably would do is, to be conservative, I would just run an independent sample t-test across these two, take a look and see if my homogeneity variance is violated, use the corrected test or whatever with that, and just run with that. So either one of these approaches would be appropriate. This just gives you a little bit extra power for your test, assuming that you've run a good design, you haven't violated any of the rules, you capitalize on that. Questions about sort of our thinking as we're working through pairwise tests as follow-ups? Okay. Independent sample t-test, I mean, this is, you just, if you've only just has, if you're just looking at, if your ANOVA just involves 1 or 2 follow-up tests, independent sample t-test is just fine. There's nothing, I mean, you can do that, no problem. If you've just got 2 tests that you're running, 2 follow-ups, your family-wise error is going to approach 0.1, but only if both null hypotheses are actually true, right? You can't make it type 1 error if the null hypothesis is false. But if it isn't, if those populations are equal, sort of at most you could have a family-wise error rate of 0.1. So it's not too bad. So just falling back on independent sample t-tests is a fine thing to do if you've got a small number of tests. And again,
I'm sorry.
Okay. And again, you can just.
Can I ask you a question?
Yep, hold up. And then we can just go through and sort of pull these out of SPSS just like we normally would anyway. Same stuff that we've done up to this point. Okay. Awesome. Yeah, Brittany.
So when you say like a priority test, this is like, I'm trying to apply this to kind of like a real world thing in my head. That's before you run, that's your like hypothesis before you run your statistics, right?
Yep.
So for example, my first year project, just trying to make this make sense in real world. Like I want to see if there's like age differences and ethnicity or race differences. These are like my 2 things that I want to think about beforehand. Mm-hmm. Right? Is this right?
Yep.
Am I thinking right?
Yep.
Okay.
Yeah.
So you only want to have, I'm just trying to understand, you only want to have like a couple of those before you start, like 1 or 2 comparisons before you start doing your stats.
Yeah. Well, I mean, This is the thing we can run into. So let's say Ari's running her thesis and she's comparing. Let's say she has 4 different conditions, right? And so with 4 different conditions, you can have 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, 3 versus 4. There are 6 different pairwise comparisons that you could make out of that set, right?
Mm-hmm.
Now, if Ari says that she has a priori hypotheses about all 6 of those,
Mm-hmm.
it starts to become quite... Now, maybe Ari does, right? But even still, with that many, there probably needs to be some correction for stuff going on, right? I've seen projects where someone has like 14 a priori hypotheses. That's probably a bit much, right?
Yeah.
So now you may have conceptual and theory-driven hypotheses about how all those things should play out, right? But the question is maybe of those, 14, which ones are the most central to your analyses, and which one of these is this is kind of the heart and soul of sort of my study. These are the other ones that are more periphery.
Okay. Makes sense. Thank you.
Yeah, good question. Other questions? All right. So this approach that we've talked about here is if I want to make pairwise comparisons, right? I want to see if group A is different than C and B is different than D and so on, and so A is different than B, okay? But sometimes what we might have is we might have hypotheses about a set of groups or some combination of groups. So it's not that I think that A and B have to be different and B and C have to be different. Maybe Riley's running a study where she's got a comparison group and then she's got 2 experimental groups, right? Let's say, Riley, you're running a treatment study and you have just kind of like a waitlist control, and then you have 2 active treatment groups, right? And what you might want to do is see whether or not the combination of these 2 groups are different than my control, right? In that case, we're talking about 3 different means, which is hard to plug into this, okay? But what we can do is we can start to set up linear contrasts. And what our contrasts do is they allow us to compare differences in means or sets of means, which gives us a more flexible approach, okay? And our contrasts are just a generalization of our t-test. What we're doing is we're still running our t-test, but what we're doing is we're just looking at different combinations of groups to compare against other combinations of groups, okay? And for my linear contrast, and hopefully no one get sort of a panic attack with subscripts and summation signs and things like this, right? But all we're doing with our contrast is we're just specifying some linear combination of means, okay? So if I say my linear combination of means is a weight of mean of group 1 plus the weighted mean of group X2 or group 2, so on and so forth. Basically, it's just a sum of the combination of the mean and the weight here. Okay. And so if we were to go through, and again, all this is saying is that what we're specifying is just a weighted sum of a set of means, right? So if, these A values here and these A subscripted values, these are just weights, okay? And if I set all of my weights equal to 1, my value for L is just a sum of my means, right? So 1 times mean 1 plus 1 times mean 2 plus 1 times mean 3 is just going to be essentially the sum of my means, okay? But if I were to set my weights equal to 1 divided by the number of means that I have, then my linear contrast is just going to be the mean of my group means, okay? So let's say that I have, 3 means, right? And so if I go 1/3 times mean 1 plus 1/3 times mean 2 plus 1/3 times mean 3, I just get the average of my 3 means, right? So we're just setting up here from our contrasts is just going to be a weighted sum of a set of means here. And so if I have a linear contrast, and we identify this with our psi symbol, we would say that my linear, that my weighted sum of means is equal to a linear contrast when the sum of all my weights is equal to 0. Okay, so if I set this up so that the sum of my individual weights sums to 0, what I've done is set up a linear contrast. Okay, so let's say I have 3 means here. I have mean 1, mean 2, mean 3. I've got 3 groups. Okay, and I say my weight for mean 1 is 1, my weight for mean 2 is -1, and my weight for mean 3 is equal to 0. Okay. If I do this, my linear contrast, and so I know that, and I know I've got a linear contrast here because if I take 1 plus -1 plus 0, I get 0. And if the sum of my weights equals 0, I've got a linear contrast on my hands. So if I go through and I apply these weights, right? If I say the value of my contrast is 1 times mean 1 plus -1 times mean 2 plus 0 times mean 3. Okay? If I run this out, what my linear contrast is giving me is basically the difference between group 1 and group 2. If I multiply 0, group 3 goes away. What I've got is mean 1 minus mean 2. What I've done is I've just specified a comparison with this set of with this set of weights. I've just specified a comparison between mean 1 and mean 2, which is then going to give me a test of the extent to which group 1, the means of group 1 and the means of group 2 are different from one another. Okay. People see what I did here? All right. Let's change this around. Okay, let's say that alternatively, I switch these up. Let's say I set my weight for A1 at 1/2, my weight for A2 at 1/2, and my weight for A3 at -1. Again, if I add if I take a half plus -1, I get 0. My weights sum to 0, which means I've got myself a linear contrast. Okay, but what am I doing with this, right? If I take 1/2 times mean 1 plus 1/2 times mean 2 plus -1 times mean 3, what I've got essentially is a difference between the average of groups 1 and 2 and group 3. Okay, and this is where we really get into our contrast. What I've done is for this second set of weights, my assumption, or sort of my test, is similar to the test that I sort of hypothetically said Riley's interested in, right? If group 3 is my control and group 1 and 2 are my 2 treatment groups, right? What I'm looking at in this contrast is I'm comparing the combination of groups 1 and 2 with group 3, okay? So what I've done is I've used these weights to set up, even though, so this ends up being, so the average of groups 1 and 2 against group 3, so it's still essentially just a t-test, right? But what I've done is I've incorporated more groups into this than just being restricted to just straight up pairwise comparisons. So people see how we're playing with these contrast weights to go through and set up some potentially more interesting comparisons that just, hey, is group A and B different? What we can do is say, I can go through with the properly set up weights. I could say, hey, what I'm interested in saying is whether groups 1 and 2 are different than the combination of 3, 4, and 5, right? And again, take the average of this, take the average of this, compare them, and now I've got a test of the extent to which 1 and 2 are different than 3 and 4 and 5. Okay, so it gives us much, much more flexibility in terms of testing things that can be relevant and interesting given the types of analyses that I'm running. Okay. All right, let's do this. Let's take a break. Let's come back at 4:10, and what we'll do is we'll go through, finish up with contrast, and then jump into some data and hopefully start showing you how to go through and test some of this stuff. Okay. All right. How we doing? People ready for the last push? Oh. I was bummed. I saw Riley reach for something. I thought she was giving me the fists up too, but she was just reaching for a water bottle. It was an incidental sort of hurrah that I saw in sort of the absence of volume. So, all right, cool. So, let's jump back in here to our contrast. Okay. Quick question: did anybody work with contrast coding? Any sort of setting up contrasts in their undergrad stat ANOVA types of things? Okay, probably not. It gets once it clicks, it sort of makes a lot of sense. But it's just one of those things that most people will not want to get into with undergraduates necessarily. But particularly from those of you from experimental traditions, like this is kind of at the heart and soul of a lot of different experimental designs and things like that. And so like this is just scratching the surface of all of this. It gets much, much more intense. We're going to give you with this just a kind of general approach to how you can tease this stuff apart that will generally be acceptable in most cases, but just be aware that there are, from that method standpoint, there's a considerably greater degree of nuance that you can go in and sort of design and stuff like that, teasing things out. Okay, so at the end of the day, what we're doing is we're just going to go through and we're going to take a set of weights. We're going to derive a set of weights to create whatever comparison that we're wanting to look at for our individual contrasts. Okay, so the big question is, how do I go through and select my coefficients to make it sort of do the thing that I want it to do? It's actually not too hard. Okay, all we need to do, 3 steps. 1, identify which set of treatments we want to compare. So which groups do we want to include in this comparison? Okay, then what we do is we can go through and assign weights as the reciprocal of the number of treatments in that set. Okay, so if I've got 2 groups versus 1 group, I just assign the group with 2. I just flip it around, so I get to assign 1/2, 1/2. The other, I got 3 beans in the other set, 1/3, 1/3, 1/3, and then I just have to assign one of those coefficients, the coefficients in one group, to be negative. And if I do that, I've got a set of coefficients that will work for my analysis. Okay, so let's say, for example, I've got 5 means, okay, x1 to x5. So I've got an experiment with 5 different conditions. And what I want to do is I want to take a look at the group, I want to run a contrast where I'm comparing groups 1 and 2 with 3, 4, and 5. Okay. So here are my means, x1, x2, 3, 4, and 5. What I'm going to do is I'm going to assign weights as the reciprocal of the number of groups, number of means within each group. So here I've got 2, so I assign those to 1/2. Here I've got 3 means, I assign 1/3, and then I just go ahead and I assign negatives to these 3 weights here. Okay, and so if I go through and if I add up my weights, 1/2 plus 1/2 minus 1/3 minus 1/3 minus 1/3, which gives me a sum of weights is equal to 0. Okay, so I know that I have a linear contrast here. And then all I need to do is I just need to sum the value of my weighted means. Okay, so I've got 1/2 times x1 plus x2 minus 1/3 plus x1, or 3, 4, and 5. I could also assign this 1/2 plus x1 plus 1/2 x2 minus 1/3 x3 minus 1/3 x4 minus 1/3 x5. I just kind of simplified my notation here a little bit. And so what if I do, if I'm taking a look at this, Allie, what have I done with this contrast? What am I comparing? Say it again.
Yes.
There we go. All right. You've got like a 5-second delay on your audio, so
Cool.
yeah. So what am I comparing in this contrast?
I mean, just groups 1 and 2 combined compared to groups 3, 4, and 5 combined.
Okay. Yeah.
Is that what you're asking?
Yep. And with this contrast, who am I? If I've set this up so that it makes sense, whose mean do I think will be higher?
1 and 2.
Yep. Okay. Which group you assign the sign to is really arbitrary. It will have no impact on your actual test. But if you assign negatives to the group, the set of means that you think will be lower, it will just make the direction of your test sort of make intuitive sense. So here, what I've done is I'm hypothesizing that the combination of 1 and 2 will be greater than the combination of 3, 4, and 5. And so I assign 1/2 and 1/2 to -1/3, -1, and -1/3. And if things work out, I'll get a positive test. If things work out in the direction that I think it should, I'll get a positive test statistic. If it's the opposite, I'll get a negative test statistic, and then I know that I predicted in the wrong direction, right? But it doesn't matter in terms of your actual test, okay? But we know that if we go through and we add this up, we get sum of the weights, we get a value of 0, telling us that we have a linear contrast. Also, something to be aware of, if I have a linear contrast that has absolute values summed to 2, this is known as a standard set, okay? So if I take 1/2, so if I add the absolute values of my weights, so if I take 1/2 plus 1/2 plus 3, plus 1/3 plus 1/3 plus 1/3, I get a value of 2, which means what I've done is I've not only specified a linear contrast here, I've created my weights so that this serves as a standard set. And this starts to become important when I'm calculating effect sizes down the road, okay? So, Robert, let's say instead of assigning weights of 1/2, 1/2, -1/3, -1/3, -1/3, let's say instead I assign weights of 3 and 3 and -2, -2, -2. Do I have a linear contrast?
No, it would end up coming out to more than 2, essentially.
Okay, so not a standard set. Do I have a linear contrast? If I assign weights of 3 and 3 and -2, -2, -2.
No, because you're not assigning the correct reciprocal of the number of trinkets in the set.
Okay, but remember that a linear contrast, anytime my weights sum to 0, I have a linear contrast. So if I do that, if I take 3 and 3 and -2 and -2 and -2, do I have a linear contrast?
Oh, yeah.
Yeah, I do, right? What if I set this to, I don't know. Basically, there's an infinite number of weights that I could assign to this, right? There's an infinite number of possibilities that get me to a linear contrast, right? But if I want that linear contrast to be a standard set, what I need is the absolute values of these to sum to 2. And so we'll talk about in some cases where it can be beneficial to use a slightly different coding system, okay? But as long as my weights sum to 0, I've got a linear contrast, and that will work. My test will work, okay? The question is then, can I use that, the value of my contrast directly in the calculation of a confidence interval or not? We'll talk about sort of where that starts to come into play, okay? But just so that you know, so if I assign 1/2, 1/2, -1/3, -1/3, and -1/3, and if I run this contrast, or if I assign 2, 2, or 3, 3, -2, -2, -2, my effect is going to be identical. It won't impact my test statistic, but it does impact the value of my contrast, okay? Which will then be used for other stuff. Okay, so note that this is kind of the traditional approach, but so again, a lot of these techniques were developed within the context of sort of experimental research, where I have people coming in, or I have conditions that I've randomly assigned, and so that I have direct control on how big or the number of individuals or observations that I have within each group. And so all of this stuff is assuming in the background implicitly that we have a balanced design. If we start to get really different cell sizes, it starts to create complications with the calculation of our contrasts and things like that. So just keep this in the back of your mind. Again, when we start to see really unbalanced designs, it starts to have impact for the calculation of statistics and assumptions and interpretations and things like that. So, classic tests for a linear contrast. If you go back through some old school books that I don't have here, but in my office, right? So like old stat texts, right? The traditional approach to calculating your test statistic for this contrast involves calculating sums of squares for your contrast. So the sum of squares for a linear contrast is just a function of the means and associated weights. So here, again, I'm calculating psi. Psi is just the value of my contrast. This is just the sum of my weighted means, right? This is the stuff that I've done already, okay? But then what I do, once I got the value of my contrast, I go through and calculate the sum of squares of my contrast. Sum of squares of my contrast is just the number of people in my cells times the square of psi over the sum of the square of my weights. Okay. We can also sort of identify this as sort of n times the sum of my weighted means squared over sort of the sum of my squared weights. Okay. If I go through and I run this out based on the weights and the means that I have put together, this gives me my sum of squares contrast. Okay. If I have an unequal sample size, my sum of squares contrast is going to be my value of my contrast squared over the sum of my square of my weight over the size of that cell. Okay, so formula changes depending on sort of I have slightly different cell sizes. Okay, so let's say I have 3 means. Okay, with 10 means in each cell. I have mean 1 is 1.5, mean 2 is 2, mean 3 is 3. Okay, and so what I want to do is I want to set A1 to 1/2, A2 to 1/2, and A3 to -1. Okay. So, Erica, what am I testing in this contrast here?
You're testing if A and B will be, like you're comparing A and B, or like 1 and 2 to 3.
Yep, perfect. And here, from my hypothesis, which one of those do I think is probably going to be bigger based on the way I've weighted these?
The sum of A and B.
Yeah, right. So basically, if I'm looking at the weights of these contrasts, I'm hypothesizing that the combination of 1 and 2 is going to be greater than the mean of group 3. Okay. So if I go through and I calculate the value of my contrast, so that's just going to be 1/2 times 1.5 plus 1/2 times 2 plus -1 times 3 gives me a value of my contrast of negative 1.25. Okay. Ari, can you give me what is it? How do I interpret this value? What does this mean?
Can I phone a friend?
Yeah. No. So okay. So it's pretty straightforward. So just looking at that value, what does that value mean? What did I do here with this? Okay, so if I take 1/2 times 1.5 and 1/2 times 2, so what did I essentially do with means 1 and 2 here?
Just combine them.
And so what is why if I break this down, if I rearrange this and take the mean of group 1 and the mean of group 2 and divide it by 2, what does that give me? Yeah, if I add groups 1 and 2 and divide it by 2, what did that give me?
Half the value.
Right, which is the... Okay. Close. So if I take groups 1 and group 2 and I add them and divide them by 2, I just took the average of groups 1 and 2, right? So here I've got the average of groups 1 and 2, and I've subtracted the mean of group 3. So my value of my contrast here, if I've got a standard set, is just the difference in the average of group 1 and 2 versus group 3. Did that kind of click? Ish, kind of, sort of. Okay. Do people see what we've done here with this standard set? When I have when the absolute value of my weights sum to 2, what I've done is the value of my contrast is literally just the difference in the average of 1 and 2 versus 3. Okay, and so this is why that standard set is helpful, is because if I look at this, I'm essentially just saying there's a 1.25 difference across the average of group 1 and 2 relative to group 3. Okay. Now I could go through and I could assign this a value of, I could assign my weights to be 2 and 2 and negative 4. Okay. Rachel, if I assign 2, 2, and negative 4, do I still have a linear contrast?
Yes.
Yeah, I do, right? But is the value of my contrast going to be the point difference between the average of group 1 and 2 and group 3?
Wait, what?
Okay.
Are you asking if it's going to be the same value?
Yeah.
No.
No, it's not, right? It's still going to be something that applies to my test, but if I go through and if I assign my weights so that they're consistent with the standard set, what it means is I basically have a difference value that's scaled in sort of my normal scale. So I can interpret this as literally what I've got is a 1.25 difference in the average of groups 1 and 2 relative to group 3. Okay? And so if I do that, then from the classic approach, what I would do is I've got the value of my contrast. And now what I'm going to do is I'm going to calculate my sum of squares contrast, which is going to be my cell size, right? So I got equal cells. I got 10 people in each cell. So I'm going to take 10 times the value of my contrast squared, which is 1.25, and square that. Right? Then I'm going to take this over the sum of my squared weights. So I'm going to take 1/2 squared plus 1/2 squared plus negative 1 squared. Run that out. It's going to give me a value of 10.42. And then, because these linear contrasts, it's a 1 degree of freedom test, right? I've got 3 different groups in here. But really all it is it breaks down into a t-test. I've got a combination of 1 and 2, and that's one group. And I've got group 3, and that's another group. And so basically, I've just got a 1 degree of freedom test, right? And because of this, my sum of squares contrast is equal to my mean squared contrast. So if I take a sum of squares divided by degrees of freedom, it gives me the mean squared. Mean squared is just a variance estimate. So what I can do is I can take the mean squared contrast that I've calculated and divide it from the mean squared error in my ANOVA to give me a test statistic. Okay, so essentially what I've got here is my mean squared for my contrast. So this is variability, the variance I'm seeing in my contrast. Over the top of my mean squared error, this is my estimate of within subjects error or within group error. This will give me an F statistic, which I can then evaluate against a critical F with 1 and degrees of freedom error from my ANOVA table. Okay, so what we've got here from the classic approach is we would test our a priori contrast against an F statistic. And that F statistic is just a function of my assigned weights and the value of my contrast. Okay. Then in the denominator, I'm just pulling the mean squared error from my ANOVA table, right? And that mean squared error, remember, Robert, what is mean squared mean in ANOVA talk?
It's the variance within groups?
Yep, it's just
MS error?
Yep, it's just the variance within group. Mean squared just means variance. So I'm taking the variance of my contrast over the variance of just my estimate of within subject error variance from my ANOVA, and it's going to give me an F test. And then I would test that F against a critical value of 1 and whatever the degrees of freedom error is from my ANOVA table, and that's going to give me my test. And then I would get an associated p-value and so on and so forth. Okay, so this is the classic approach to going through and running out a test. So if you were to look in old textbooks or in certain programs, you'll see linear contrast tested with an F statistic. Okay. But when we go through and we get them in SPSS, what you'll see in SPSS when we request contrasts is that they give us contrasts as a T statistic. Okay, and this is probably the formula I would recommend that you run for different assignments and things like that, just because it's going to be a little bit easier, given some stuff that's going to go on. Here, what we're going to do is we're just going to take, for your T, is just going to be your the value of your contrast over standard error of your contrast. Standard error of your contrast is just going to be calculated as the mean squared error from your ANOVA table times the sum of your squared weights over the sort of number of people in that cell. Okay, it's a little bit faster, it's a little bit more efficient. Your T critical is just going to be your test statistic, or two-tailed test statistic with degrees of freedom from consistent with your mean squared error. And if I've got a design that's fully balanced, right? If I have equal people in each cell, that classic F and the SPSS, the T statistic that you get, the T statistic that you get through SPSS they're going to be identical tests, right? One will be an F and one will be a T, but the p-value will be identical. So here, again, what we're doing is we're just calculating the value of our contrast, like we did here, okay? But then what I'm going to do is I'm just going to calculate a standard error estimate for that contrast, and that's just going to be my mean squared error from my ANOVA table plus the sum of my squared weights over sort of the samples. So here it's going to be, let's say, if we go back to sort of this, right? And I wanted to test my white non-Hispanic group against these two others, right? My weights then I would assign, let's say I'm assuming that my participants who identified as white non-Hispanic are going to find this report higher levels of valence than sort of my other groups. My weights would be 1, -1/2, -1/2, right? And so then what I would do for this, I would just take 1 squared divided by 41 plus -1/2 squared divided by 38 plus -1/2 squared over 20, and that would just be the sum of my squared weight, or the sum of my squared weights divided by the number of people per cell. Okay, this just gives you a little bit more flexibility in terms of unequal sample sizes to go through and calculate some of this stuff. So, what we also get in SPSS is some corrected tests and standard errors if I have violations of homogeneity of variance. Okay. And how SPSS does this, I had to go through and dig and try and find the formulas exactly what SPSS is doing with their corrected tests. Essentially, it's a modification in the calculation of the standard error and modification of the calculation of the degrees of freedom. And so you get a test statistic that's the value of your contrast over your modified standard error, and a T critical that's tested against a modified degree of freedom. And so SPSS will provide, just like it does with independent sample t-tests, right? You have homogeneity, equal variances assumed, equal variances not assumed, which if you're looking at it will make you happy because it makes it look as though you've corrected for potential violations of homogeneity of variance. In actual fact, I've not been able to find independent sources saying that this is a thing in the methods literature. So it's obviously something that SPSS has came up as a corrected test for this. I haven't been able to independently verify that this is a thing that is a good thing or an accepted thing, but it's a thing that SPSS does. This is sort of something that, and SPSS is the program that everybody uses, and so this is kind of what people report. But just so to know that at least I wasn't able to independently verify, I had to do a lot of digging to exactly figure out exactly what was going on here. So just kind of take that with a grain of salt. All right. All right. So people see at least kind of the underlying formulas for how we're calculating these contrasts, how we're assigning weights, how we set up comparisons, and at least how we go through and use these formula to go through and do stuff. So for your purposes, for our purposes here, this stuff, this is just sort of FYI, so you know if you run into literature where contrasts are reported as F tests, this is what they're doing. Just know that that's from like an old school, like crank it out by hand, like this is how things go. For our purposes, this is probably going to be the more efficient way to go through and do stuff. Okay. All right. So if I've got my planned contrast, how do I go through and manage that family-wise error? Okay. Again, traditionally what we will do is we'll look at these planned contrasts at per comparison error rates, right? Because I've called my shot and I'm getting credit for calling my shot ahead of time before I look at the data. But there are some concerns with inflated family-wise error. Again, if I've got 4 contrasts, which would be a reasonable sort of number of a priori comparisons to sort of lay out there, my family-wise error starts to approach 0.2, assuming the null hypothesis for all those contrasts is true, which may or may not be the case. I don't know, it kind of depends on the situation. And so some people will have some additional continuing concerns that even with this small set of comparisons that we may have problems with type 1 error. Okay. So 2 solutions. One, we can reduce the number of contrasts. Brittany, this is going, if you have, for your first year project, if you have 10 a priori contrasts, I would probably recommend that you reduce the number of a priori contrasts to make that a more specific set that's a little bit easier to talk about, right? But maybe you say, can't do it. All of these are important. What we might want to do is then start to set a more stringent alpha to start to manage that family-wise error, okay? And for planned contrasts, the way we would do this is we could use a Bonferroni test. Basically what Bonferroni does, it just gives a correction for my family-wise error. I set a new alpha. My alpha prime is just my alpha level divided by the number of comparisons that I've set up. Okay. So basically, if I've got 4 comparisons, right, that I want all 4 of those comparisons at alpha equals 0.05, right, I just take 0.05, divide that by 4, it sets my new alpha level at 0.0125. I didn't need to shove the calculator in your face. I did it anyway. As soon as I started to do it, I was like, that's not necessary, but I was kind of committed, so I did it anyway. The only thing we need to do with Bonferroni is we just adjust the critical, or what our criteria is for alpha, okay? So if I have 4 a priori comparisons, and I say I'm going to give it a Bonferroni correction, all I'm going to do is I'm assuming that my per comparison error rate across those 4 is alpha 0.05. So I just take alpha 0.05 divided by 4. That gives me a new alpha of 0.0125, and that's my new thing that I have to hit, okay? And don't make Bonferroni corrections more complicated than they are. All you're doing is now when I run through my tests, I look at my p-value, and if my p-value is less than 0.0125, then I can claim evidence for an effect. If it's not, then I can't. All we're doing is we're changing alpha. I just set a new alpha, set a Bonferroni alpha across those 4 tests. You're not changing the test statistic, you're not changing critical values, you're not doing anything. You're still running the test the way you would always run the test. You've just got a new critical alpha that you're comparing against. Okay? People understand that? Okay, so don't try and create a different test statistic. Don't try and sort of adjust your critical T or anything along those lines. You're just running your tests like you would normally run them, but your new p-value is at 0.05. For these 4 tests, it's 0.0125. Okay. Give me a thumbs up if you understand that. Nothing. Okay. Because we got a slow increase in sort of partial participation. So, okay. If you run into problems, let me know. But Bonferroni is easy. All we're doing is we're changing that alpha. And so, again, this is Bonferroni is just based on the assumption that, or the sort of the Bonferroni inequality. We know that the probability of one or more events can exceed the sum of their individual probabilities. So, again, if I'm saying I want my alpha level to be 0.05 per comparison, okay, yeah, the probability of one type 1 error across 3 can exceed 0.10 or 0.15. Okay, so with our Bonferroni, we would use this as a correction for a small number of planned contrasts. Okay, and I say this because it's important. This is a correction that was intended to correct for a small number of planned contrasts, or a small number or set of tests. This is not a let's correct for everything under the sun, okay? Because this is what will happen is sometimes you'll get, like Riley, you're publishing your thesis. You send it out there. You've got everything put together. And you get a reviewer that wants you to Bonferroni correct for 15 different analyses. Tell that reviewer that they're a dummy, and that would be a stupid thing to do. This is not the correction that you use for 15 analyses, right? If we're doing post-hoc comparisons, we don't apply Bonferroni because it's going to be far too stringent. It's going to be put far more of a correction on there than you would want. This is intended to correct for a small number of comparisons. If we're being very, very careful, it's easy to apply because let's say I have 10. I have 10 pairwise comparisons. I take 0.05 and I divide it by 10. And that's my new alpha, and then I compare everything against that. But it sets the bar way too high. I'm going to make way too many type 2 errors on that. And so it's not to be used for post hocs. It's just for a small set of a priori comparisons. Other thing we can do, we can use a Dunn-Sidek. Dunn-Sidek, it's sort of similar to Bonferroni. It just gives a more precise correction for family-wise error. Instead of just taking my alpha level and dividing by the number of comparisons, I'm setting my alpha to 1 minus 1 minus alpha times taken to the 1 over the number of comparisons power. Dunn-Sidek, Bonferroni are going to be very similar in terms of the alpha level that you get. Dunn-Sidek just provides just a modest and sort of more precise control over Bonferroni. And so if you want to be cool, kid, like I did Dunn-Sidek instead of Bonferroni because it's more precise, probably won't make a huge amount of difference. Sort of, we're talking about inches here, but it's a different approach so that you can go through and use. Okay, but again, with both of these, we're setting a new alpha to correct for this set of comparisons. Questions on this? Okay. So we'll finish up here with sort of quick touching on confidence intervals and effect sizes for my contrasts. Okay. So again, we're going to say that I've gone through and I've run my overall omnibus test. Okay, and my omnibus test says, yeah, you've got some differences somewhere within these groups. And so what I do is I say, okay, well, I've got sort of these 3 a priori contrasts that I'm going to run because these are the things that I think are important that make sense given my given my question, and so these are the specific comparisons I'm going to run. You go through and you make those comparisons, but what we might want to do, like anything else, is try and get a sense for the precision of my estimates, right? So I say that the combination of groups A and B are going to be different than group C. Okay, so I can go through and I can run that, and I'll get a value of my contrast that tells me if I calculate it correctly, it'll tell me, yeah, the combination of group A and B is 4.5 points larger than group C. Okay, but still, I might want to know, well, what are supported based on my data? What are supported values for that difference? Because maybe that starts to make sense or starts to become important, right? Let's say, Eric, I'm just trying to think, going back like some like let's say sort of some of Ben's anger research, right? And we've got a couple different manipulations to sort of elicit anger or something like that, right? And so let's say we've got 2 versus sort of the standard in the field. Like everybody uses this one, but I've got 2 other ones that I think are pretty good. And so I want to know, okay, so yeah, I get sort of 4 points higher on sort of this anger scale for this the combination of these 2 manipulations versus the other one. But if I'm going to go through and I'm going to do this again and again and want to use this, I might want to say, sort of what are the ranges I can expect for an increase over sort of the industry standard on this, right? Well, this is again where our confidence interval starts to come in. Confidence interval, not too bad. And this is where calculating your contrast using this T statistic starts to come in handy, because it gives you a standard error estimate that you can then use to calculate your confidence interval. So your confidence interval, again, before, our classic formula for confidence interval is just mean 1 minus mean 2 plus or minus my critical T times my standard error, right? Here, I'm just taking my value of my contrast plus or minus my critical T times my standard error. It's the same stuff that we've been doing up to this point. No different. Interpretation is the same. Nothing changes. It's all the same stuff. We're just kind of pulling it from different points. Okay. So again, yeah, my standard error here is just going to be the same standard error that I use to test my specific contrast. Do that, it's going to give me a confidence bound. Okay. My effect size, again, as with all of my pairwise effects, kind of the tricky thing that I need to get into is what's my standardizer. Okay, what do I use to go through and standardize this effect? The calculation of my effect size is exactly the same as it has been for our other tests. For a pairwise comparison, it's just going to be mean 1 minus mean 2 over probably my pooled variance, or the square root of my pooled variance, or my pooled standard deviation. I have this as D, but that's just a general, this is essentially a G statistic, right? Or what I can do is if I have a contrast, right? If I have more than 2 groups, now what I need to do is start thinking carefully about what do I go through and use as my standardizer, okay? So a few different options. What I'm saying here is I've got the value of my contrast over an error standard deviation here, okay? Depending on my design, I can sort of go through and pull different things. If I've got, let's say, Allie's conducted a beautiful, fully balanced experimental study where we've got the same number of people in each cell, or fairly close to the same number of people in each cell, no evidence of violation of homogeneity of variance. What I can use is my standardizer. I can just take the square root of my mean squared error from my overall ANOVA table. Okay. Remember that your mean squared error from your overall ANOVA table is just a combination, or it's essentially your pooled variance across your individual groups. Okay. It's just sort of one, again, assuming that I have relatively equal samples and I don't have any violations of homogeneity of variance. My the mean squared error in my ANOVA, that's just the pooled variance across all of my cells. It's just a nice representative estimate of my error variance that capitalizes on the full design. That can be a nice figure to use if I haven't had any violations of assumptions or things. Okay, but let's say I am worried about homogeneity of variance. Let's say that I do have evidence of violation of homogeneity of variance based on my Levine's test. What I might do is I might not be super interested in using this pooled variance, because maybe I've got 4 groups and this individual contrast is looking at groups 1 versus 3 and 4. I don't know what leaving 3 or 2 out of it does here. So if I'm worried about homogeneity of variance, what I can use if I've got a balanced design is the square root of the average variances of my samples in question, right? So if I'm looking at 1 versus 3 and 4, what I could do is I could take the averages of variance, assuming I have equal people or equal number of cell sizes across those. I just take the average of variance of 1, 3, and 4, and then take the square root of that. That would be fine if I'm worried about homogeneity of variance. Okay, because maybe it is group 2 that's got a crazy high variance or a crazy small variance, but I'm not interested in them, but they're actually getting calculated in the mean squared error, so I don't want to use that. So I'm going to go through and use the average variance across sort of the means or the groups that are being included in my individual contrast. Okay. Or let's say maybe I'm worried about unequal N and homogeneity of variance. So I've got an unbalanced design. I got different numbers of people in different groups, right? And it's pretty noticeable discrepancy in terms of my cell sizes. I know that cells with more people are going to give me a more precise estimate of my variance than cells with less people. So I want to take into account what I can do then is take the square root of my pooled variance of my sample in question here. Okay, and what I'm doing is just going through and taking let's see. If I'm going through and remember, so my pooled variance here, this is just going to be n minus 1 times my variance for 1 plus n2 minus 1 for variance 2 plus n3 minus 1 for variance 3, so on and so forth, right? And then so we got n1 plus n2 plus n3, and in this case it would be minus 3. Okay, so we're just taking that pooled variance formula and extending it out to include sort of more than 2 means, right? And so what we're doing here is we're just taking the weighted taking the weighted average of these variances, recognizing that we've got different cell sizes that is going to produce some variability in sort of the precision of those estimates, right? And so a different approach that we can take with that. Okay. Or at the end of the day, we always have standard deviation in my control group, right? If I've got a group that I'm going through and want to use, so this is the standard, this is the basic, this is the state of existence in nature without us fooling around with anything. This can be a nice interpretable effect or a standardizer to use because it just kind of ties everything together and talks about standard deviation units in terms of sort of where people are just naturally. So if I've got a clear baseline or control condition, using the standard deviation of that control is always a fair thing to do. All right. Last thing to note here. Up here for my confidence interval formula and in sort of my effect size here, we've got just the value of your contrast as what we're plugging into here. Only thing to remember is that our coefficients have to form a standard set in order for us to just drop the value of the contrast in there, right? If I go through and I set my weights to be equal to something aside from whatever a standard set, right? So for my contrast, right, for my actual test, if I want to compare the combination of groups 1 and 2 to group 3, I could set these as 1/2, 1/2, -1. And that gives me a standard set. The absolute value of those weights sum to 2, so I've got a standard set. And with that, I can take the value of my contrast and drop that in for my effect size and for my, for my confidence interval for my effect size. But if I don't, I can go through and I can have, I can set my weights to be 1, 1, and -2. That still gives me a linear contrast. My test the p-value for my test will be identical to what it was with this first set of weights. It's just I don't have a standard set, and so the value of my contrast I can't interpret it literally as the difference between the combination of this group and the combination of these groups. It's not, it screws up the scale, And so there are cases where we might do that, and we'll talk about that next week, and we'll have an example where I can set up. SPSS is kind of limited in sort of the level of decimal places it will take in terms of my weights, and so it starts to fool around with things a little bit. So I might decide not to use a standard set. I just need to recognize that I can't use the value of that contrast in my confidence interval or my effect size just because it's not scaled to my actual data. Okay. And we'll go through examples of this. If that doesn't make sense right now, hold tight. We'll get in there until next week, and then it still might not make sense. But at that point, you can tell me and say, hey, explain this more. So, okay. Questions about any of this? All right, cool. So what we'll do is we'll stop there. We will finish up or start in next Wednesday with some data. We'll go through the planned contrast set, and we'll go through and sort of talk about how to get these contrasts out of SPSS and make sure that we know how to go through and interpret, calculate confidence intervals and things like that. So we'll do that, talk about post hoc tests, and then depending on sort of how quickly we move through that, maybe start in on factorial ANOVA stuff. Okay. So that's kind of where we're at. Does that sound all right? Okay, cool. We're getting close. I'm happy with our timeline. I think we're gonna do. We'll be pretty good with stuff. Get those power calculations in by Friday at noon to CJ. So there won't be any syntax files or anything like that. It'll just be your write-up and your appendices that you'll send off to CJ. So make sure to get those in by the deadline. And then our next set, the ANOVA set, won't be due until, I guess, what did we say, like the 7th? Or the 30th? Is that what we said, or did we talk about that?
You said that problem set 6 would be due the 4th, and then 7 would be due the 11th. Right? Because I was talking about.
Okay. Okay. So we'll finish up here. Okay. Yeah, that works. Yeah, that'll be fine. Okay. Yeah, we'll finish up. So you'll be working on sort of this while we're still sort of going through sort of factorial ANOVA stuff, but that'll be fine. I guess the only thing that'll do is then we'll have your last set, the factorial ANOVA stuff, will be due on the 11th, so the last day of finals. So that kind of puts those two kind of back to back with one another. But if you're concerned about your timeline, anything like that, always remember that you can turn these things in sort of way ahead of time early. And so just however you want to sort of manage your time, we'll do that. We'll say that the last set, the factorial set, there's just kind of a lot of pieces and components to it. So if you get that other one done early, it'll sort of help you out and sort of give you some sort of a little bit more breathing room on that. But sort of however you want to manage it, that's perfectly sort of okay with me. Sound good? Okay, cool. Awesome, everybody. Thanks for hanging in there. Thanks for dealing with sort of people trying to come through my roof. But hopefully, yeah, they'll be done next time, so we won't have rat-a-tat-tat going on top of my roof. It's like really obnoxious Santa Claus, but not really. But all right. We'll see you guys. Have a good night. And let me know if you run into any questions. All right. Bye.